Hi, I'm Alan, an engineer from Maxim Integrated, and today I'm going to talk about duty cycle in buck converter and how it will affect the output voltage regulation. The duty cycle of a buck converter is the percentage of the time that the converter is in the on state relative to the switching period. It is also the output voltage divided by the input voltage. The input voltage is affected by inductor resistance, high side FET resistance, and other parasitic resistance. These resistances will decrease the input voltage, which leads to a longer on-state and higher duty cycle. When the part's maximum duty cycle is reached, the available input voltage limits the output voltage that can be regulated. I will demonstrate the effects of the maximum duty cycle of the output regulation using EESIM OASIS. For my design, I am going to use MAX 20098. The MAX 20098 has a maximum duty cycle of 97%. My design will have an input voltage of 12 volts, an output voltage of 10 volts, a load current of 20 amps, and a switching frequency of 400 kHz. After loading MAX 20098 onto EESIM OASIS, we first change the V-in voltage source to 12 volts. Then we set the initial condition to our input caps, CN1, to 12 volts. Then set CN2 initial condition to 12 volts. Since this is an external resistor feedback part with feedback of 1 volt, we'll change the resistors R4 to 10k ohms, then R3 to 90.9k ohms. Now we need to update initial condition and load source to get us 20 amps of load current. First, we double click on load and we change the start current to 20 amp and pulse current to 20 amp. Then we change the source resistance to 0.5 ohms. Then we set the initial condition to our inductor to 20 amps. Now we need to set the parameters for our ICU1. Change the switching frequency to 400 kHz. And change our ROSC to 60.5 kilo ohms. Let's hit simulator and run simulation. The duty cycle in this case should be 10 volts over 12 volts, or 83.3%. Let's zoom in on the plot. As you can see, we have a period of about 2.28 microseconds. And an on-state time of about 2.09 microseconds. This corresponds to an average duty cycle of 91.7%. This is also larger and greater than the expected 83.3%. Seems like the simulated results produces a larger duty cycle than the ideal duty cycle. In this case, the duty cycle did not reach the maximum duty cycle of 97%. So the output voltage is still regulated and is at 10.1 volts. What if I purposely set the input voltage lower to say 10.7 volts and simulate again? The duty cycle should increase with lower input voltage. Although the theoretical duty cycle should be 10 volts over 10.7 volts or 93.5%, from the previous simulation, the real duty cycle should be larger. On EESIM OASIS, let's change V-in to 10.7 volts. And then let's update our initial conditions for CN1 and CN2 to 10.7 volts. Now press simulator and run schematic. This time, looking at the output voltage, this is not 10 volts and instead is 9.68 volts. This means that the real duty cycle has surpassed the maximum duty cycle of 97%. The duty cycle is capped and cannot drive past the 97%, and it fails to regulate or maintain at the output voltage of 10 volts. Since my desired output voltage is 10 volts, and I cannot increase the duty cycle above 97%, the input voltage must be increased to achieve regulation. How do I do that?
Here are some of the parts that were picked for the design. A coil-craft inductor with a DCR of 5.7 milliohms, and a Fairchild FET with RDS(on) of 36 milliohms. I'm going to take a closer look at these parts on the schematic. Since there are current flowing through the parts, the component resistances will cause a voltage drop from the input voltage. Perhaps changing the inductor and FET and lowering their parasitic resistance parts will reduce the effect on the drop on the input voltage. For the new design, I will use a different set of inductor and FET. I will use coil-craft inductor with DCR of 1.65 milliohms and an on-semi FET with RDS(on) of 17.6 milliohm. Back to our model. Now I'll replace my FET and inductor. First, the FET, and I'm gonna go here and grab the new FET and replace it. Now I'm gonna replace my inductor, delete it, and copy it, and go back and replace it. And now I will simulate again. All right, after simulating, we go to output voltage and we zoom in. And here we can see that the output voltage is regulated and it's around 10 volts.
From the previous inductor and FETs, the output is not regulated correctly and has an output voltage of 9.68 volts. The duty cycle was at maximum and capped. In the second set of inductor and FET, with the lower component resistance helped the duty cycle to be closer to our expected value, and it is regulating. This shows that the duty cycle is heavily affected by the parasitic resistance. The effective input voltage decreased because of the FET's RDS(on) and inductor's parasitic resistance. If these resistances reduce the input voltage such that the maximum duty cycle is reached, then the part will not regulate. With eSIM OASIS, it is easy to pick and choose the components and verify that the real duty cycle and the part's operation. This can avoid potential problems before it is too late.